High above you, at this exact moment, particles are arriving from space at nearly the speed of light. They pass through the upper atmosphere, collide with atoms of nitrogen and oxygen, fracture into showers of new particles, and continue downward. Some of those fragments reach sea level. Some pass through concrete, steel, and glass. A small fraction pass through your body without leaving any sensation at all. This is not a rare event. It is continuous. Every second, an invisible rain of high-energy particles is striking Earth from all directions, depositing energy, triggering nuclear reactions, and briefly altering the microscopic state of the matter they encounter. These particles are known as cosmic rays, although they are not rays in the usual sense. They are individual particles, mostly protons and atomic nuclei, moving with extreme energies that far exceed anything naturally produced on Earth. At ground level, several thousand secondary particles created by cosmic rays pass through each square meter every minute. At higher altitudes, that number increases dramatically. Commercial aircraft cruise through regions where cosmic ray intensity is tens of times higher than at sea level, and astronauts beyond Earth's magnetic shield experience an environment dominated by this particle radiation. Yet for most of human history, none of this was noticed. There was no light, no sound, no heat, no immediate biological signal that could be sensed directly. The reason cosmic rays feel so abstract today is the same reason they remained hidden for so long. They interact weakly, sporadically, and invisibly with ordinary matter. A single cosmic ray proton can pass through a human body without damaging a single cell. When interactions do occur, they happen at scales far smaller than human perception, inside atoms and nuclei, without instruments sensitive to electric charge, ionization, and subatomic motion. The universe's particle rain leaves no obvious trace. Despite this invisibility, cosmic rays are not rare visitors. They are a fundamental background of the universe, produced wherever matter is accelerated to extreme energies. They have been present since the earliest generations of stars exploded, since magnetic fields first twisted charged particles into violent trajectories, and likely since the first large-scale structures formed. Earth has been immersed in this flux for its entire existence. The atmosphere, the magnetic field, and the planet's own mass act together as a protective filter, but they do not block cosmic rays completely. Instead, they reshape them. As a cosmic ray enters the upper atmosphere, typically at altitudes above 15 kilometers or about 9 miles, it collides with a nucleus in the air. That single collision initiates a chain reaction. New particles are created: pions, kaons, muons, electrons, photons, each carrying a fraction of the original energy. These secondary particles spread outward in a widening cascade known as an air shower. By the time the cascade reaches the surface, it may cover an area hundreds of meters across. The original particle is gone, but its energy has been redistributed into a complex, fleeting web of interactions. This process happens constantly. The reason it does not feel dramatic is statistical. The atmosphere is vast, and the interactions are sparse relative to the scale of everyday matter. Most of the energy carried by cosmic rays is deposited high above the ground. What reaches us is a diluted remnant. Still, even at sea level, muons, heavy cousins of electrons created in these air showers, pass through your body at a rate of roughly 1 per square centimeter per minute. They are born high in the atmosphere and survive long enough, thanks to relativistic time dilation, to reach the ground before decaying. None of this was known before the 20th century. For centuries, physicists believed that space beyond Earth was largely empty and inert, a vacuum punctuated only by light from distant stars. Radiation, when it was considered at all, was assumed to originate locally, from radioactive materials in the ground, or from atmospheric electricity. The idea that energetic particles were constantly arriving from deep space had no observational foundation. There was simply no reason to suspect it. The first cracks in this picture appeared indirectly, through experiments that had nothing to do with astronomy. In the late 18th and early 19th centuries, scientists studying electricity noticed a persistent problem. Charged objects left in isolation gradually lost their charge, even in dry air and carefully controlled conditions. This leakage could not be fully explained. The prevailing assumption was that air itself was slightly conductive, but the rate of discharge was higher than expected. Something was ionizing the air, knocking electrons off atoms and allowing charge to dissipate. As experimental techniques improved, this unexplained ionization became more puzzling. Electroscopes, instruments designed to detect electric charge, consistently showed spontaneous discharge even when shielded from known sources of radiation. The effect persisted indoors and outdoors, day and night. Attempts to eliminate it by improved insulation failed. Whatever was causing the ionization appeared to be everywhere. For decades, the most reasonable explanation seemed to be terrestrial radioactivity. After the discovery of radioactive elements, it was natural to assume that trace amounts in the soil and atmosphere were responsible for ionizing the air. This explanation worked partially, but not completely. Measurements taken underground showed reduced ionization, but not zero. Measurements taken at higher elevations produced unexpected results. If radiation were coming from the ground, ionization should decrease steadily with altitude. In some cases, it did not. At the time, the instruments were crude by modern standards. Ionization chambers and electroscopes provided indirect measurements, integrating many effects into a single signal. Distinguishing between different radiation sources was difficult. There were no particle detectors, no electronic counters, no way to identify individual events. The problem was not a lack of curiosity, but a lack of tools. Another obstacle was conceptual. The energies involved in cosmic rays are enormous, far beyond what classical physics of the 19th century had reason to anticipate. The idea that space itself could supply particles with energies millions or billions of times greater than those produced by chemical reactions was foreign. Even after the discovery of radioactivity, the known energies were modest compared to what cosmic rays would later reveal. Without a theoretical framework that allowed for extreme acceleration mechanisms, the notion of high-energy particles from space seemed unnecessary. As a result, the early clues were interpreted conservatively. The unexplained ionization was treated as an experimental nuisance rather than a window into a new physical phenomenon. Progress was slow and incremental. Measurements improved. Shielding was refined. Data accumulated. But the underlying assumption that all significant radiation sources were local remained largely unchallenged. What finally shifted the perspective was not a single dramatic observation, but a gradual pattern that refused to disappear. Ionization levels did not behave as expected with altitude. They did not correlate cleanly with known radioactive sources. They showed a baseline that could not be eliminated. This background was real, persistent, and global. Before we go deeper, if you enjoy exploring the quiet mechanics of the universe like this, consider subscribing and leaving a comment with where you're listening from and what time it is there. It helps this channel grow, and it keeps these long scientific journeys alive. The realization that something unknown was permeating the atmosphere marked the beginning of cosmic ray physics, even though the term itself had not yet been coined. The phenomenon existed long before it was named. Earth was already embedded in a high-energy particle environment shaped by astrophysical processes far beyond the solar system. The challenge was not to create the signal, but to recognize it for what it was. What makes this early phase of discovery especially striking is how completely cosmic rays defied human intuition. They arrived silently. They did not illuminate the sky or warm the ground. They left no macroscopic scars. Their presence could only be inferred statistically through tiny electrical effects measured over long periods. Even then, the signal was subtle enough to be dismissed repeatedly. This invisibility is still part of their character today. Modern detectors can trace individual air showers, reconstruct energies, and estimate arrival directions, but cosmic rays remain elusive. Unlike light, they do not form images. Unlike sound, They do not propagate as waves through familiar media. Their paths are bent and scrambled by magnetic fields, erasing direct information about their origins. They announce themselves only through interaction. The invisible rain continues regardless of observation. It does not depend on Earth's awareness or technology. It is a natural consequence of energetic processes throughout the universe. Exploding stars, turbulent magnetic fields, and violent environments capable of accelerating particles to extraordinary speeds. Earth happens to sit in the path of this flux, shielded but not isolated. Understanding how this realization emerged requires following the gradual refinement of measurement and interpretation, from crude electroscopes to high-altitude experiments that would eventually demonstrate beyond doubt that the radiation ionizing Earth's atmosphere was arriving from above. The path from unexplained discharge to cosmic origin was neither fast nor obvious. It unfolded through careful observation, persistent anomalies, and a willingness to question assumptions about where energy in the universe could come from. At this stage in the story, nothing has yet been traced to a star, a galaxy, or a distant explosion. There are no sources, no spectra, no maps of the sky. There is only a background effect that refuses to vanish. The atmosphere is being ionized by something not fully accounted for by Earth itself. The rain is falling, even if no one yet knows where it begins. By the early years of the 20th century, the unexplained ionization of air had become a persistent irritation for experimental physicists. Electroscopes continued to discharge even under careful shielding. Measurements underground reduced the effect, but did not eliminate it. At modest elevations, the behavior was inconsistent. If radiation were coming from the ground, the signal should weaken steadily with height. In several cases, it did not. The question was no longer whether something was happening, but where it was coming from. The decisive step required leaving the ground entirely. In 1912, an Austrian physicist named Victor Hess undertook a series of balloon flights designed to answer a deceptively simple question. Does atmospheric ionization increase or decrease with altitude? Balloons were not new to science. Meteorologists had already used them to probe temperature, pressure, and humidity. What Hess proposed was more dangerous and far less forgiving. He would carry sensitive electroscopes thousands of meters into the atmosphere, far above any known terrestrial radiation source, and measure the ionization rate directly. At the time, this was not a routine experiment. Balloons were fragile, navigation was imprecise, and oxygen deprivation was a real risk. Instruments had to function reliably despite cold, vibration, and low pressure. Hess flew repeatedly, refining his methods, improving shielding, and repeating measurements under different conditions, including at night, to rule out solar effects. The logic behind the experiment was straightforward. If the ionizing radiation came primarily from radioactive materials in Earth's crust, then increasing altitude should reduce exposure. The farther one moved from the ground, the weaker the radiation should become. If, on the other hand, the radiation came from above, then ionization should increase with height once the shielding effect of the lower atmosphere diminished. Early balloon measurements, before Hess had produced ambiguous results. Some showed a slight decrease in ionization at low altitudes, consistent with terrestrial radiation fading with distance. Others hinted at stabilization, or even mild increases higher up. But the data were noisy and often dismissed as instrumental error. Hess's contribution was persistence and altitude. He went higher than anyone before him, and he went back repeatedly. As his balloon ascended beyond 1 kilometre, about 0.6 miles, the expected decrease did occur at first. Ionization levels dropped slightly, reinforcing the assumption that Earth-based radiation was a contributor. But as the balloon climbed further, the trend reversed. Above roughly 2 kilometres or 1.2 miles, the ionization rate began to rise. By the time Hess reached altitudes above 5 kilometres, about 3.1 miles, the ionization was significantly higher than at ground level. This was not a subtle effect. The increase was large enough to overwhelm uncertainties in the instruments. It persisted across multiple flights. It appeared during the day and at night, eliminating the sun as a dominant source. No known terrestrial radiation source could explain an increase with altitude of this magnitude. The implication was unavoidable. A substantial component of the ionizing radiation was coming from above the atmosphere. This conclusion ran directly against prevailing assumptions. Space was not supposed to be a source of penetrating radiation. Stars emitted light and heat, but particles energetic enough to ionize air deep in the atmosphere were not part of standard astrophysical thinking. Hess himself was cautious in interpretation, but the data spoke clearly. Earth was being bombarded by radiation of extraterrestrial origin. What made the result especially compelling was its simplicity. Hess did not rely on complex theory or indirect inference. He measured a single quantity, ionization rate, as a function of altitude. The trend was monotonic beyond a certain height. There was no plausible terrestrial mechanism that could produce increasing radiation with distance from the ground. Within a few years, the result was independently confirmed. Other balloon experiments reached similar conclusions. The term cosmic rays was introduced to describe this mysterious radiation from space, even though its true nature was still unknown. At the time, it was widely assumed to be high-energy electromagnetic radiation, akin to gamma rays, but far more penetrating. That assumption would later prove incorrect, but it was a reasonable first step. The energies implied by Hess's measurements were extraordinary. The radiation penetrated deep into the atmosphere and even into enclosed spaces. Whatever it was, it carried far more energy per particle than typical radioactive emissions. The birth of cosmic ray physics did not occur with fanfare. There was no single moment of revelation, no immediate understanding of sources or mechanisms. Instead, the field emerged from a narrow experimental anomaly that refused to disappear. Hess's flights transformed an experimental nuisance into a fundamental discovery. Earth exists within a continuous flux of high-energy radiation from space. The significance of this shift cannot be overstated. For the first time, astrophysics intersected directly with particle physics. The universe was not just something to observe remotely through light. It was actively delivering particles to Earth, carrying information about energetic processes far beyond the solar system. At the same time, the discovery raised more questions than it answered. What kind of radiation was this? How was it produced? How could space accelerate particles to such extreme energies? The known physics of stars and planets offered no obvious mechanisms. Complicating matters further was the behavior of the radiation itself. Unlike light, cosmic rays did not arrive from specific directions in a simple way. Early measurements suggested that the radiation was nearly isotropic, arriving equally from all directions. This isotropy hinted at either very distant sources or strong deflection by magnetic fields, neither of which was yet understood. The realization that cosmic radiation increased with altitude also reframed Earth's atmosphere. It was no longer just a passive envelope of gas, it became an active detector, transforming incoming cosmic particles into secondary cascades that could be measured at the surface. The atmosphere itself was part of the experiment. As balloon technology improved, flights reached higher altitudes, refining the picture further. Ionization continued to rise well above the levels explainable by any terrestrial contribution. The conclusion solidified. the dominant source of this radiation lay beyond Earth. In 1936, Victor Hess was awarded the Nobel Prize in Physics for his discovery. By then, the field he helped create had expanded dramatically. New detectors had begun to reveal that cosmic rays were not gamma rays at all, but charged particles, mostly protons, deflected by magnetic fields. Cloud chambers showed curved tracks rather than straight lines. The picture grew more complex and more interesting. But at the moment of discovery, none of that was known. What mattered was altitude. Height broke the illusion that Earth was isolated from the energetic universe. By lifting instruments above the ground, Hess exposed a constant, invisible connection between Earth and distant astrophysical processes. This discovery also marked a philosophical shift. Nature was no longer neatly divided into terrestrial and celestial domains. Processes occurring far beyond the Milky Way could influence measurements made inside a small balloon over Europe. The boundary between laboratory physics and cosmic physics dissolved. From this point forward, cosmic rays would become tools as well as mysteries. Before particle accelerators existed, cosmic rays would provide access to energies unattainable on Earth. They would reveal new particles, test theories, and force revisions of fundamental physics. All of that lay ahead. For now, the key realization was simple and profound. The unexplained ionization of air was not a flaw in experimental technique. It was evidence of a universe far more energetic than previously imagined, continuously interacting with Earth from above. By the time the radiation from above was firmly established as real, a new problem emerged immediately. What exactly was arriving at Earth? The word ray carried assumptions. In the early 20th century, radiation meant waves, X-rays, gamma rays, electromagnetic energy propagating through space. It was natural to imagine cosmic rays as an especially penetrating form of light. That interpretation did not survive contact with better instruments. As detection techniques improved, the radiation from space revealed a defining feature that electromagnetic waves do not possess. It carried electric charge. This realization came from a simple but decisive observation. When cosmic radiation was allowed to pass through magnetic fields inside cloud chambers and early detectors, the tracks curved. The curvature depended on the strength of the magnetic field and the momentum of the incoming particle. Light does not curve in this way. Charged particles do. The universe was not sending rays, it was sending matter. What we call cosmic rays are individual particles, mostly the familiar building blocks of ordinary atoms, accelerated to extraordinary energies and launched across interstellar and intergalactic space. About 90% of them are protons, the nuclei of hydrogen atoms stripped of their electrons. Roughly 9% are heavier atomic nuclei, ranging from helium all the way up to iron and beyond. The remaining fraction consists of electrons, positrons, and trace amounts of rarer species, including antiprotons and exotic isotopes. This composition immediately revealed something profound. Cosmic rays are chemically ordinary. They are not made of unknown substances or exotic matter. They are the same particles found in Earth's atoms and molecules. What distinguishes them is not what they are, but how fast they are moving. A typical cosmic ray proton travels at a speed extremely close to the speed of light. In many cases, its kinetic energy exceeds its rest mass energy by factors of thousands or millions. For the most extreme events, that factor reaches 10 billion or more. At those energies, the particle's behavior is governed by relativistic physics. Time dilation becomes significant. Interactions probe subnuclear scales. A single particle can carry as much kinetic energy as a well-thrown baseball, concentrated into a region smaller than an atomic nucleus. This enormous range of energies is one of the defining features of cosmic rays. At the low end, some cosmic rays overlap with energies achievable in human-made particle accelerators. At the high end, they exceed anything produced on Earth by many orders of magnitude. The cosmic ray energy spectrum spans more than 12 orders of magnitude, from billions of electron volts to more than 10 to the 20th electron volts. No other known natural phenomenon exhibits such a continuous and extended energy range. To understand how these particles are observed, it is essential to distinguish between primary and secondary cosmic rays. Primary cosmic rays are the particles that arrive at the top of Earth's atmosphere directly from space. These include protons, heavier nuclei, electrons, and antiparticles. They are the original messengers, carrying information, often scrambled, about their distant origins. Secondary cosmic rays are created when primary cosmic rays collide with atoms in Earth's atmosphere. These collisions are violent. A single high-energy proton striking a nitrogen nucleus can produce dozens of new particles in a fraction of a microsecond. The products include pions, kaons, muons, neutrinos, electrons, photons, and short-lived resonances that decay almost immediately. By the time the cascade reaches sea level, most of what remains are muons. Muons are heavier versions of electrons, about 200 times more massive, and they are remarkably penetrating. Because they interact weakly with matter and are born moving near light speed, they can travel kilometers through air and hundreds of meters through rock before decaying. Nearly all of the cosmic radiation that reaches your body at ground level consists of muons produced high in the atmosphere by primary cosmic rays that never reach the surface themselves. This distinction matters because most detectors on Earth do not see primary cosmic rays directly. The atmosphere acts as both a shield and a converter. It protects life from the most damaging radiation, but it also transforms incoming particles into showers that can be measured over large areas. Understanding cosmic rays therefore requires reconstructing the properties of the primary particle from the debris it leaves behind. The charged nature of cosmic rays introduces another critical complication. Charged particles do not travel in straight lines through space. They are deflected by magnetic fields, those of stars, galaxies, and intergalactic space. Even Earth's magnetic field plays a role, guiding lower-energy cosmic rays toward the poles and shielding equatorial regions more effectively. This is why cosmic ray intensity varies with latitude and altitude. Because of this magnetic deflection, cosmic rays lose directional information. By the time a proton arrives at Earth, its path may have been bent thousands of times over millions of years. Tracing it back to its source is often impossible. Unlike photons, which preserve their direction unless scattered, cosmic rays arrive, scrambled. They tell us that extreme accelerators exist, but they rarely point directly to them. The presence of antimatter among cosmic rays adds another layer of interest. Antiparticles such as positrons and antiprotons are observed in small but measurable quantities. These are not signs of exotic antimatter regions of the universe. Instead, they are produced naturally when high-energy cosmic rays collide with interstellar gas or with atoms in Earth's atmosphere. The creation of matter-antimatter pairs is a standard outcome of high-energy particle interactions predicted by quantum field theory and confirmed in laboratories. What makes antimatter in cosmic rays valuable is not its existence, but its proportion. Deviations from expected ratios could signal new physics, such as dark matter annihilation or unknown particle processes. For this reason, measuring the composition of cosmic rays with high precision has become a major experimental goal. The chemical makeup of cosmic rays also carries information about their history. The relative abundance of different nuclei, hydrogen, helium, carbon, oxygen, iron, differs slightly from that found in the solar system. These differences reflect the processes that accelerate and transport cosmic rays. Heavier nuclei, for example, are more easily confined by magnetic fields and may spend longer times propagating through the galaxy, undergoing spallation reactions that fragment them into lighter elements. Some rare isotopes found in cosmic rays are unstable and decay on timescales comparable to their travel time through the galaxy. By measuring their abundance, scientists can estimate how long cosmic rays have been wandering through interstellar space. The answer is typically millions of years. Cosmic rays are not fresh emissions arriving directly from nearby sources. They are ancient travelers diffusing through the galaxy for vast periods before encountering Earth. The term cosmic ray, then, is a historical artifact. It reflects an early misunderstanding that persisted long enough to become entrenched. By the time the particle nature of the radiation was established, the name had already taken hold. Today, it remains useful as a label, even though it obscures the true nature of the phenomenon. This misnomer has consequences beyond semantics. It shapes intuition. Rays suggest beams, directions, and imaging. Particles suggest collisions, diffusion, and randomness. Cosmic rays behave much more like a gas of relativistic particles filling the galaxy than like rays emitted from point sources. Their arrival directions are nearly isotropic. Their flux is steady on human timescales. Their interactions are governed by probabilities rather than trajectories. At the same time, cosmic rays are not uniform or featureless. Their energy spectrum contains structure. Their composition varies subtly with energy. Their intensity changes with solar activity, as the solar wind modulates the lower energy component entering the inner solar system. These details encode information about acceleration mechanisms, magnetic turbulence, and large-scale astrophysical environments. Understanding what cosmic rays actually are also reframes their role in physics. For decades, before particle accelerators reached high energies, cosmic rays were the primary source of high-energy particles for laboratory study. Muons, pions, and other particles were first discovered in cosmic ray experiments. Entire branches of particle physics were built on observations made using photographic plates carried to mountaintops or exposed at high altitudes. Even today, cosmic rays probe energy regimes beyond the reach of the largest accelerators. They test physical laws under extreme conditions. They interact with matter at center of mass energies far exceeding those produced at facilities like the Large Hadron Collider. They offer a natural laboratory that cannot be turned off, only interpreted. At this point in the story, cosmic rays have shed their disguise. They are no longer mysterious rays from the heavens, but a flux of familiar particles behaving in unfamiliar ways. They are shaped by relativistic motion, magnetic fields, and violent astrophysical environments capable of imparting staggering amounts of energy to ordinary matter. What remains unresolved is how these particles acquire such energies in the first place, how they propagate through the tangled magnetic architecture of the galaxy, and how the rarest, most energetic examples originate. The particles themselves are known, their origins are not. The moment a high-energy cosmic ray reaches the upper atmosphere, it stops being a single particle and becomes a process. What arrives from space is usually a lone proton or atomic nucleus, moving so fast that, from its own perspective, the distance between stars is compressed by relativity. What it encounters, however, is a dense forest of air molecules. At altitudes above roughly 15 kilometers, or about 9 miles, the first collision occurs, and from that instant onward, the atmosphere itself becomes a particle factory. The collision is not gentle. A primary cosmic ray proton strikes the nucleus of a nitrogen or oxygen atom, with energies far exceeding those that bind nuclei together. The target nucleus shatters. New particles are created. Momentum and energy are redistributed into a spray that expands downward and outward at nearly the speed of light. This is the birth of an extensive air shower. The first products of these collisions are typically unstable particles called pions. Pions come in 3 varieties: positively charged, negatively charged, and neutral. They are not components of ordinary matter and do not survive long. At rest, they decay in a tiny fraction of a second. At relativistic speeds, their lifetimes are stretched by time dilation, allowing them to travel measurable distances before decaying. Neutral pions decay almost immediately into gamma-ray photons. These photons carry enormous energy and can trigger further interactions, producing electron-positron pairs and initiating electromagnetic cascades. Charged pions, by contrast, decay primarily into muons and neutrinos. This branching sets the structure of the entire air shower. The neutrinos produced in these decays are almost impossible to stop. They interact so weakly with matter that nearly all of them pass straight through Earth without leaving any trace. Trillions of them are passing through your body every second, created not only by cosmic rays in the atmosphere, but also by nuclear reactions in the sun and distant astrophysical sources. They are part of the cascade, but they do not contribute to what we experience at the surface. Muons are different. They are heavier cousins of electrons, with about 200 times the mass. This extra mass makes them far less prone to radiative energy loss as they pass through matter. They are charged, so they interact electromagnetically, but they do not shower the way electrons do. Instead, they punch through. A muon born high in the atmosphere typically travels at more than 99.9% of the speed of light. At rest, a muon decays in about 2 microseconds. Without relativity, this would limit its travel distance to a few hundred meters. In reality, because of time dilation, the muon's internal clock runs slower relative to Earth. From our frame, it lives long enough to travel tens of kilometers. Many reach sea level. Some penetrate deep underground. By the time an air shower develops fully, it is split into distinct components. The electromagnetic component consists of electrons, positrons, and gamma photons produced primarily by neutral pion decay and subsequent interactions. This part of the shower spreads laterally and is largely absorbed by the atmosphere before reaching the ground, especially at lower energies. The hadronic component contains surviving protons, neutrons, and heavier fragments that continue to interact and generate further pions. This component drives the growth of the shower, but also fades with depth as energy is lost and particles are absorbed. The muonic component is the most penetrating. Muons retain a large fraction of the original cosmic rays energy and travel in relatively straight lines. At ground level, they dominate the particle flux. When you stand at Earth's surface, nearly all of the cosmic radiation passing through you consists of muons created tens of thousands of feet above your head. These cascades are not rare. They occur continuously across the entire planet. Every second, somewhere above you, a primary cosmic ray is triggering a shower. The size of the cascade depends on the energy of the initial particle. Lower energy cosmic rays produce small showers involving a handful of secondary particles. Ultra-high energy cosmic rays can generate cascades that spread across several square kilometers, briefly turning the atmosphere into a massive natural particle detector. Despite their scale, these showers are fleeting. From first collision to ground impact, the entire process unfolds in microseconds. The atmosphere returns to equilibrium almost instantly. There is no lingering glow, no persistent disturbance. Only instruments sensitive to subatomic events can register that anything happened at all. The reason secondary particles can reach the ground lies in a balance between interaction and decay. Electrons and photons interact strongly with air, losing energy rapidly through scattering and radiation. Neutrons decay or collide. Pions decay quickly. Muons, however, occupy a sweet spot. They are heavy enough to resist radiative losses, charged enough to be detected, and long-lived enough, thanks to relativistic effects, to survive the journey downward. This is why muons pass through buildings, mountains, and human bodies with ease. A typical muon at ground level can traverse several meters of concrete or hundreds of meters of rock before stopping. It does not see matter the way macroscopic objects do. It interacts with individual electrons and nuclei, occasionally ionizing atoms along its path, but losing only small amounts of energy per interaction. In practical terms, this means that muons routinely pass through you without consequence. The radiation dose from cosmic ray muons at sea level is small compared to natural background radiation from radioactive elements in the Earth. At higher altitudes, however, the effect becomes significant. Airline crews and frequent flyers receive higher doses because they spend long periods in regions where the atmosphere provides less shielding and muon flux is higher. The penetration power of muons has turned them into scientific tools. By measuring how many muons pass through an object from above, researchers can infer its internal structure. This technique, known as muon tomography, has been used to image the interiors of volcanoes, search for hidden chambers in pyramids, and monitor nuclear reactors. The same particles that quietly pass through your body can map the density of entire geological formations. From a physical standpoint, air showers represent a bridge between astrophysics and particle physics. The initial interaction probes energies far beyond those accessible in laboratories. The subsequent cascade involves well-understood particle processes, decays, scattering, pair production, playing out on a planetary scale. Every shower is a natural experiment conducted by the universe, using Earth's atmosphere as both target and detector. The structure of these cascades also encodes information about the original cosmic ray, the number of particles, the lateral spread, the ratio of electromagnetic to muonic components, and the depth at which the shower reaches maximum intensity all depend on the energy and mass of the primary particle. A heavy nucleus behaves differently from a proton. An ultra-high-energy event leaves a different signature than a modest one. This is how scientists study cosmic rays without ever seeing the primary particle directly. They reconstruct the invisible from the debris. Arrays of detectors spread across large areas sample the shower front as it reaches the ground. Fluorescence telescopes observe faint ultraviolet light emitted when air molecules are excited by passing particles. Together, these methods allow researchers to estimate the energy and arrival direction of the original cosmic visitor. What makes this remarkable is that the atmosphere itself is doing most of the work. Without it, Earth would be directly exposed to primary cosmic radiation, with far more severe biological consequences. With it, the radiation is softened, redistributed, and partially filtered. Life exists beneath a shield that is not opaque but transformative. The sky above us is not empty. It is an active medium where high-energy physics unfolds constantly, invisibly and impartially. Cascades bloom and vanish without notice. Muons rain down through walls and flesh alike, indifferent to human presence. The universe announces its energy not with flashes or noise, but with a steady, silent rain of particles that only careful measurement can reveal. By the time it became clear that cosmic rays were particles rather than rays, a deeper challenge emerged. These particles were invisible, fleeting, and unpredictable. They could not be stored, aimed, or switched on. They arrived one by one, scattered across the planet, leaving behind only subtle traces of their passage. To study them required a new kind of physics, one that inferred the properties of unseen events from the smallest possible signals. The first successful tools were almost deceptively simple. One of the earliest was the cloud chamber, developed in the early 20th century by Charles Wilson. The principle was elegant. A sealed chamber filled with supersaturated vapor would condense into tiny droplets along the path of an ionizing particle. Where the particle passed, a thin line of mist would appear, briefly revealing its trajectory. For the first time, invisible radiation could be seen. When cosmic rays passed through these chambers, the results were startling. Instead of straight, unbroken tracks expected from photons, researchers saw curved paths bending in magnetic fields. Some tracks suddenly forked, stopped, or spawned secondary paths. Entire cascades of particles appeared from a single incoming event. The cloud chamber transformed cosmic rays from abstract ionization rates into visible physical processes. It confirmed decisively that these were charged particles interacting with matter. As technology advanced, cloud chambers were supplemented and eventually replaced by more practical detectors. Scintillators became central to cosmic ray research. These materials emit brief flashes of light when struck by charged particles. The light can be collected by photomultiplier tubes and converted into electrical signals. Each pulse corresponds to a particle passing through. Scintillators are fast, robust, and scalable. They can operate continuously and be spread across large areas, making them ideal for studying air showers. With scintillators, cosmic ray detection moved from individual tracks to statistics. Instead of watching one particle at a time, researchers could count rates, coincidences, and timing differences across multiple detectors. If several detectors triggered simultaneously, it indicated the passage of a shower rather than a single particle. This coincidence technique allowed scientists to map the footprint of air showers at ground level. Another key phenomenon made cosmic rays measurable in a different way: Cherenkov radiation. When a charged particle travels through a medium faster than light can propagate through that medium, not faster than light in vacuum, but faster than light in air, water, or glass, it emits a faint cone of blue light. This is not a violation of relativity. It is analogous to a sonic boom produced when an object exceeds the speed of sound in air. In Earth's atmosphere, high-energy electrons and positrons in cosmic ray showers can exceed the local speed of light in air, producing Cherenkov flashes. These flashes are extremely brief, lasting only nanoseconds, but they are detectable. On the ground, specialized telescopes equipped with fast photodetectors can capture this light and reconstruct the direction and intensity of the incoming shower. Cherenkov radiation provides two critical pieces of information. First, it confirms the presence of relativistic charged particles. Second, the geometry of the light cone encodes the direction of the original shower. By measuring the arrival time of the light at different detectors, scientists can infer the angle at which the primary cosmic ray entered the atmosphere. As cosmic ray energies increased, individual detectors were no longer sufficient. The most energetic events are so rare that only a handful strike a given square kilometre per year. To capture them, researchers built vast air shower arrays, networks of detectors spread across tens or hundreds of square kilometres. Each detector samples a tiny fraction of the shower front. Together, they reconstruct the whole. One of the defining examples of this approach is the Pierre Auger Observatory, located in Argentina. It covers an area larger than some cities, using thousands of surface detectors combined with fluorescence telescopes that watch the sky at night. When an ultra-high energy cosmic ray strikes the atmosphere, the resulting shower triggers many detectors almost simultaneously. The timing and signal strength across the array reveal the energy, direction, and approximate mass of the original particle. Fluorescence detection adds another layer. As charged particles pass through the atmosphere, they excite nitrogen molecules, causing them to emit faint ultraviolet light. This fluorescence traces the development of the shower as it grows and then fades with altitude. Unlike surface detectors, fluorescence telescopes can observe the shower's longitudinal profile, how it evolves as it penetrates deeper into the atmosphere. This profile is crucial. The altitude at which the shower reaches its maximum intensity depends on the energy and composition of the primary cosmic ray. Protons tend to penetrate deeper before reaching maximum development. Heavier nuclei interact earlier and produce showers that peak higher in the atmosphere. By measuring this depth, researchers can infer whether the incoming particle was light or heavy. Reconstructing energy is a process of inference rather than direct measurement. No detector captures the full energy of a cosmic ray. Instead, energy is estimated from proxies, the total number of particles at ground level, the intensity of fluorescence light, the spread of the shower footprint, and the timing structure of the signals. These observables are compared against detailed simulations based on known particle physics. Direction reconstruction relies on timing. When a shower front reaches the ground, it does not arrive everywhere at once. Detectors closer to the shower axis trigger slightly earlier than those farther away. By measuring these time differences with nanosecond precision, scientists can fit a plane or curved surface to the arrival times and determine the direction of the incoming particle to within a degree or better. This precision is remarkable given the scale involved. The original interaction may occur 20 kilometers, or about 12 miles above the ground. The primary particle itself is never observed. Yet from the timing and intensity of secondary particles spread across kilometers, its properties can be inferred. Cosmic ray detection has also moved beyond Earth's surface. Balloon-borne experiments and satellite missions carry detectors above the atmosphere to measure primary cosmic rays directly. These instruments use magnetic spectrometers, calorimeters, and time-of-flight systems to identify particle charge, mass, and energy. They complement ground-based observations by providing clean measurements unaffected by atmospheric cascades. Despite these advances, cosmic ray measurement remains fundamentally statistical. Individual events are unpredictable. The highest energy particles may arrive once per century per square kilometre. Detectors must operate continuously for years to accumulate meaningful data. This patience is built into the field. Cosmic ray physics progresses not through bursts of discovery, but through steady accumulation. What makes measuring the invisible especially challenging is that interpretation depends on models of particle interactions at energies beyond laboratory testing. Simulations rely on extrapolations of known physics. When discrepancies appear between observations and models, it is not always clear whether the issue lies in astrophysical assumptions or in particle physics itself. Cosmic rays probe regimes where the two domains overlap. This ambiguity is not a weakness. It is a source of power. By studying cosmic rays, scientists test fundamental physics under conditions unattainable on Earth. Deviations from expectations can hint at new phenomena, unknown interactions, or gaps in understanding. Every detector is both an astronomical instrument and a particle experiment. The atmosphere, once an obstacle, has become part of the apparatus. It converts invisible primaries into observable showers. The ground becomes a sampling surface. The night sky becomes a faint screen glowing briefly with ultraviolet traces of passing energy. Measuring the invisible is no longer about seeing particles directly, but about learning to read their footprints. By building detectors that respond to light, timing, and coincidence, physicists have turned Earth itself into a cosmic ray observatory. The rain continues to fall, unnoticed by the senses, but recorded in flashes, pulses, and patterns. Each measurement is a reconstruction, a careful inference drawn from fragments. And from those fragments, a picture of the energetic universe slowly emerges. Long before cosmic rays reach Earth, long before they fracture the atmosphere into cascades of secondary particles, they must first be accelerated. This is the central problem of cosmic ray physics. Ordinary matter does not spontaneously acquire enormous energies. Protons do not drift into relativistic motion by chance. Somewhere in the galaxy, natural engines exist that are capable of taking common particles and pushing them to speeds within a fraction of light itself. The leading candidates for this role are supernova remnants. When a massive star reaches the end of its life, gravity wins. The core collapses in milliseconds, and the outer layers rebound outward in a violent explosion. For a brief moment, the star releases as much energy as the sun will emit over its entire lifetime. What remains is an expanding shell of gas and magnetic fields racing into the surrounding interstellar medium at thousands of kilometers per second, several thousand miles per second. This expanding shell is not just debris, it is a shock wave, and shock waves are efficient accelerators. A shock front is a boundary where physical conditions change abruptly. Density, temperature, velocity, and magnetic structure all jump sharply across a thin region. In supernova remnants, the shock propagates outward for tens of thousands of years, ploughing through interstellar gas. Charged particles caught in this environment experience repeated encounters with turbulent magnetic fields on either side of the shock. Each encounter can increase their energy. This process is known as diffusive shock acceleration. Despite the technical name, the underlying idea is simple. A charged particle crosses the shock front, scatters off magnetic irregularities, and crosses back again. Each time it crosses, it gains a small amount of energy from the bulk motion of the shock. The particle does not gain energy all at once. It gains it incrementally through thousands or millions of crossings. Over time, these small gains accumulate. The efficiency of this mechanism is remarkable. It naturally produces a power law energy distribution, meaning that there are many low-energy particles and progressively fewer high-energy ones, exactly matching the observed shape of the cosmic ray spectrum over a wide range of energies. No fine-tuning is required. The mathematics of repeated random acceleration at a moving boundary leads inevitably to this result. Magnetic fields are essential to this process. Without them, charged particles would simply stream away from the shock after a single encounter. The interstellar medium, however, is threaded with magnetic fields, and the shock itself amplifies them. As particles are accelerated, they generate turbulence in the magnetic field around the shock, creating a chaotic environment that traps them. This self-generated turbulence allows particles to cross the shock again and again, extending the acceleration process far beyond what would otherwise be possible. In this sense, supernova remnants are not passive explosions. They are dynamic systems that restructure their surroundings. They convert kinetic energy from the expanding blast into non-thermal particle populations. A significant fraction, on the order of 10% of the explosion's energy, is believed to go into accelerating cosmic rays. This efficiency is high enough that supernovae occurring at the observed rate in the Milky Way can account for the total energy density of galactic cosmic rays. This conclusion is not based on theory alone. It is supported by multiple lines of observation. X-ray telescopes have revealed thin, bright filaments at the edges of supernova remnants. These filaments are produced by synchrotron radiation, emitted when relativistic electrons spiral around magnetic field lines. The sharpness of the filaments implies strong magnetic fields and rapid energy losses, both signatures of active particle acceleration. Gamma-ray observations provide even more direct evidence. When accelerated protons collide with surrounding gas, they produce neutral pions, which decay into gamma-ray photons. These photons carry characteristic energy signatures that distinguish them from gamma rays produced by electrons. Observations of several supernova remnants show exactly this pattern, indicating that not only electrons, but also protons are being accelerated to high energies. This matters because protons dominate the cosmic ray population. Electrons radiate energy quickly and cannot travel far through the galaxy. Protons are more stable. They survive long enough to diffuse through interstellar space and eventually reach Earth. Any viable source of galactic cosmic rays must therefore accelerate protons efficiently, not just electrons. Supernova remnants meet this requirement. The scale of these accelerators is vast. A typical remnant expands to tens of light years across, filling a volume far larger than any human-made device. The shock persists for thousands of years, providing ample time for acceleration. The magnetic turbulence extends well beyond the visible shell, shaping particle motion on scales comparable to the size of the remnant itself. Despite this success, there are limits. Supernova remnants can accelerate particles only up to a certain maximum energy. This limit arises from a combination of factors: the size of the remnant, the strength of the magnetic field, and the speed of the shock. As the remnant expands and slows, its ability to confine and accelerate particles diminishes. Eventually, the highest energy particles escape, diffusing into the galaxy. This escape process is not a failure. It is essential. Escaping particles seed the galactic cosmic ray population. Over millions of years, they spread throughout the Milky Way, scattering off magnetic irregularities and gradually losing directional information. By the time they reach Earth, they carry no clear memory of their birthplace, only the imprint of the acceleration process itself. Observations suggest that supernova remnants can account for cosmic rays up to energies of around 1 quadrillion electron volts, a feature in the spectrum known as the knee. Beyond this energy, the situation becomes less certain. Either supernova remnants operate more efficiently than currently understood, or additional sources contribute at higher energies. This question remains open. What is clear is that the galactic environment is not quiet. It is filled with overlapping shockwaves from generations of stellar explosions. Magnetic fields are constantly stirred and amplified. Charged particles wander through this turbulent sea, gaining and losing energy over timescales far longer than any human history. The Milky Way functions as a slow distributed accelerator powered by stellar death. X-ray and gamma-ray astronomy have been crucial in revealing this picture. Instruments operated by organizations such as NASA and international partners have allowed scientists to trace non-thermal radiation back to specific remnants and shock structures. These observations connect the microphysics of particle acceleration to the macroscopic evolution of galaxies. The galactic engine does not aim its output. It does not produce beams. It fills space with energetic particles in all directions. The result is a steady background rather than a flash. Cosmic rays are not fireworks. They are exhaust. Understanding this engine reframes cosmic rays not as anomalies but as inevitable byproducts of how galaxies evolve. As long as stars form and die, shocks will propagate. As long as magnetic fields exist, charged particles will scatter and accelerate. The cosmic ray rain is not an accident. It is a consequence. By the time these particles leave their birthplaces, they have already interacted with magnetic turbulence, shock fronts, and interstellar gas. They carry with them a fossil record of violent astrophysical processes encoded in their energies and composition. Earth intercepts only a tiny fraction of this flux, but that fraction is enough to reveal the workings of the galactic engine that never truly turns off. By the time a cosmic ray leaves its birthplace, whether that birthplace is a supernova remnant or some other energetic environment, its journey has already become complicated. It is not launched into empty space. It enters a galaxy filled with magnetic structure. Weak by everyday standards, but powerful enough over vast distances to dominate the motion of charged particles. From that moment on, the particle's path is no longer a straight line. It becomes a walk through a magnetic maze. The Milky Way is threaded with magnetic fields on many scales. There is a large-scale, coherent component that roughly follows the spiral structure of the galaxy, and there is a turbulent component, tangled and irregular, generated by stellar winds, supernova explosions, and the motion of ionized gas. Typical field strengths are only a few microgauss, millions of times weaker than a refrigerator magnet. But cosmic rays are sensitive not to field strength alone, but to field strength multiplied by distance. Over thousands of light years, even weak fields exert decisive control. A charged particle moving through a magnetic field experiences a force perpendicular to both its velocity and the field direction. This force does not slow the particle down. It bends its trajectory. The result is a curved path, often approximated as a spiral around magnetic field lines. The tighter the spiral, the more strongly the particle is confined. The tighter the confinement, the longer the particle remains inside the galaxy. How tightly a cosmic ray spirals depends on a quantity known as rigidity. Rigidity is the particle's momentum divided by its electric charge. A particle with high rigidity is hard to bend. One with low rigidity is easily deflected. This means that rigidity, not just energy, determines how a cosmic ray moves through magnetic fields. A proton and an iron nucleus can carry the same total energy, but their rigidities will be very different. The iron nucleus has a much larger electric charge. As a result, it is more strongly affected by magnetic fields and follows a more tortuous path. Electrons, being much lighter and equally charged, are deflected even more strongly and lose energy rapidly through radiation. This is why high-energy electrons do not travel far from their sources, while protons and nuclei can wander the galaxy for millions of years. The energy of the particle also matters. At low energies, cosmic rays are tightly bound to magnetic field lines. Their paths resemble random walks, scattering repeatedly off magnetic turbulence. At higher energies, the spiral radius increases. The particle becomes less confined, sampling larger regions of the galaxy with each turn. Eventually, at sufficiently high energy, the particle's path approaches a straight line over galactic scales. This gradual transition has profound consequences. For most cosmic rays detected at Earth, the deflection accumulated over their journey is enormous. A proton, with energy typical of the bulk cosmic ray population, will have its direction scrambled completely long before it reaches the solar system. By the time it arrives, any memory of where it came from has been erased. This is why cosmic rays do not point back to their sources. Unlike photons, they cannot be traced along straight lines through space. Their arrival directions are nearly isotropic, with only subtle variations that require enormous datasets to detect. Even if a supernova remnant were accelerating particles nearby, the cosmic rays reaching Earth would arrive from all directions, indistinguishable from the background. The magnetic maze does not end at the edge of the galaxy. Intergalactic space also contains magnetic fields, weaker and less well understood, but still capable of deflecting charged particles over millions of light years. For cosmic rays of extragalactic origin, these fields add another layer of uncertainty. The longer the path, the greater the scrambling. This deflection places a fundamental limit on cosmic ray astronomy. Astronomy traditionally relies on direction. Telescopes collect light and reconstruct images. Cosmic rays deny us that simplicity. For most of their energy range, they carry almost no usable directional information. They tell us that powerful accelerators exist, but not where they are. There are exceptions at the highest energies. As rigidity increases, deflection decreases. Ultra-high energy cosmic rays, those with energies millions of times higher than those produced by supernova remnants, are bent less by magnetic fields. For these rare particles, the maze begins to open. Their arrival directions show hints of anisotropy, slight clustering that may point back, approximately, to nearby extragalactic structures. Even here, the situation is delicate. Magnetic fields in and around the galaxy still distort trajectories. The paths are not straight, just less tangled. Reconstructing origins requires modelling magnetic fields that cannot be measured directly. Small uncertainties in field strength or structure translate into large uncertainties in inferred source locations. Rigidity also introduces composition dependence. A proton and a heavier nucleus with the same energy will arrive differently. Protons point back more cleanly. Heavy nuclei smear out more. If the composition of ultra-high energy cosmic rays changes with energy, as observations suggest, then directional studies become even more complex. An apparent clustering could reflect changes in composition rather than true source locations. The Sun adds yet another layer. The solar wind carries its own magnetic field, creating a heliosphere that modulates lower energy cosmic rays entering the inner solar system. This solar modulation varies with the 11-year solar cycle, altering the intensity and energy distribution of cosmic rays detected at Earth. At low energies, this effect dominates, masking any galactic signal entirely. All of this means that cosmic ray astronomy is statistical rather than pictorial. Instead of images, researchers analyze distributions. They look for small deviations from isotropy, correlations with large-scale structures, energy-dependent changes in arrival directions. The signals are subtle and require long observation times and large detector arrays. The magnetic maze also acts as a storage system. Cosmic rays do not stream freely out of the galaxy. They are trapped, bouncing from field to field, gradually diffusing outward. This confinement increases the cosmic ray energy density inside the Milky Way far above what would be expected if particles escaped immediately. It also smooths out temporal variations. A nearby supernova does not produce a sudden spike in cosmic ray intensity at Earth. Its contribution is spread out over tens of thousands of years. This smoothing has consequences for life. It means that Earth experiences a relatively steady background rather than catastrophic bursts. The magnetic maze, combined with the atmosphere, turns violent astrophysical events into a manageable drizzle. Without it, cosmic radiation would be far more variable and far more dangerous. From a scientific perspective, however, this same protection is frustrating. The very mechanisms that make cosmic rays safe also make them hard to interpret. Each particle that arrives has followed a unique, chaotic path, shaped by fields we cannot fully map. No two journeys are the same. This does not make cosmic rays useless as messengers. It changes what they can tell us. Instead of pointing to individual sources, they reveal global properties. The shape of the energy spectrum reflects the balance between acceleration, confinement, and escape. The relative abundances of different nuclei encode information about propagation times and interaction histories. The degree of isotropy constrains the structure and strength of galactic magnetic fields. In this way, cosmic rays act as probes of the invisible architecture of the galaxy. They respond to magnetic fields that cannot be seen directly. Their behavior places limits on how turbulent those fields must be, how extended, how strong. Even the absence of clear directional information is itself information. The maze metaphor is not merely descriptive, it is literal. The galaxy is filled with pathways that guide, trap, and redirect charged particles over immense distances. Cosmic rays do not travel through space so much as they diffuse through it, step by step, deflection by deflection. Only at the very highest energies do some particles begin to escape the maze with their directions partially intact. These rare messengers sit at the boundary between cosmic ray physics and traditional astronomy. They hint at a regime where charged particle astronomy may become possible, at least in a limited sense. For the vast majority of cosmic rays, however, the maze remains closed. They arrive at Earth anonymous, stripped of directional identity, carrying only their energy and charge as clues. The challenge of cosmic ray science is to learn how to read those clues, knowing that the path itself can never be fully retraced. If cosmic rays arrived with a single characteristic energy, understanding them would be straightforward. They do not. Instead, they arrive spanning an enormous range, from particles with energies comparable to those produced in terrestrial accelerators, to particles so energetic that a single one carries macroscopic amounts of kinetic energy. When scientists count how many cosmic rays arrive at each energy and plot that number against energy, a remarkably simple pattern emerges, one that holds across more than 12 orders of magnitude. The cosmic ray energy spectrum follows a power law distribution. In practical terms, this means that low-energy cosmic rays are common and high-energy cosmic rays are rare, with the number falling off smoothly as energy increases. On a logarithmic plot, the spectrum appears as a nearly straight line over a vast range. This is not an arbitrary shape. Power laws arise naturally from processes involving repeated stochastic energy gains. Exactly the conditions present in diffusive shock acceleration. In a power law spectrum, there is no preferred energy scale. The same physical process operates across many decades of energy, producing a continuous distribution rather than a peak. This immediately distinguishes cosmic rays from thermal processes, where particles cluster around a characteristic energy set by temperature. Cosmic rays are non-thermal. Their energies are not determined by equilibrium, but by acceleration and escape. Over most of the observed range, the spectrum declines roughly as energy raised to a negative power slightly steeper than -2. That steepness encodes how efficiently particles are accelerated and how quickly they escape their environments. A flatter spectrum would indicate more efficient acceleration or stronger confinement. A steeper one would imply faster losses or weaker trapping. The observed slope is consistent with particles gaining energy in shocks and gradually leaking out of the galaxy. This broad regularity, however, is not the whole story. Embedded within the smooth decline are subtle but significant features, breaks where the slope changes. These features are known as the knee and the ankle, and they mark transitions in the origin and behaviour of cosmic rays. The first major feature appears at energies around 1 quadrillion electron volts. At this point, the spectrum steepens slightly. This bend is called the knee. Below the knee, cosmic rays are abundant enough to be studied in detail. Above it, their numbers drop more rapidly with energy. The existence of the knee suggests a physical limit. One interpretation is that it reflects the maximum energy to which typical galactic accelerators, most notably supernova remnants, can accelerate protons. As particles approach this limit, they escape more easily from their acceleration sites and from the galaxy itself. The result is a reduction in the flux at higher energies. There is additional evidence supporting this view. Measurements of cosmic ray composition indicate that, above the knee, the average mass of incoming particles increases. Lighter particles, such as protons, appear to drop off first, while heavier nuclei persist to somewhat higher energies. This behaviour is exactly what would be expected if acceleration and confinement depend on rigidity. Heavier nuclei with higher charge have higher rigidity at the same energy and can be confined and accelerated more effectively. In this picture, the knee is not a single cutoff, but a sequence of cutoffs. Protons reach their maximum energy first, followed by helium, carbon, oxygen, and eventually iron. The combined effect produces a smooth steepening rather than an abrupt end. The knee thus encodes information about both acceleration mechanisms and galactic magnetic confinement. As energy increases further, another transition appears. At around 1 quintillion electron volts, the spectrum flattens again. This feature is known as the ankle. Here, the decline becomes less steep, suggesting the emergence of a new population of cosmic rays. The ankle is widely interpreted as the point where extragalactic cosmic rays begin to dominate over galactic ones. Below the ankle, the Milky Way's magnetic fields are effective at confining charged particles. Above it, even heavy nuclei have such high rigidity that they escape more readily. The galaxy becomes transparent to them. Particles arriving at Earth with these energies are likely to have originated outside the Milky Way. This transition is not merely geographical. It reflects a change in acceleration environments. Galactic sources such as supernova remnants struggle to reach these energies. Extragalactic sources, such as active galactic nuclei, powerful jets, or large-scale shocks, operate on much larger spatial and temporal scales, making higher energies possible. Beyond the ankle, the spectrum continues its decline, but with new physics entering the picture. At the highest energies observed, cosmic rays interact not only with magnetic fields and matter, but with the background radiation that fills the universe. As ultra-high-energy particles travel through intergalactic space, they encounter photons from the cosmic microwave background. At sufficiently high energies, these encounters become energetic enough to produce new particles, draining energy from the cosmic ray. This process leads to a predicted suppression in the spectrum at the very highest energies, sometimes referred to as a cutoff. The existence of such a suppression has been observed, though its detailed interpretation remains an active area of research. Whether it reflects energy losses during propagation, intrinsic limits of acceleration, or a combination of both is still debated. What unites all these features is rarity. Extreme energies are rare, not because the universe is unwilling to produce them, but because producing them requires exceptional conditions. Acceleration to high energy takes time, size, and magnetic structure. The particle must remain confined while gaining energy repeatedly. It must avoid losing energy through radiation or collisions, and once accelerated, it must survive a long journey without catastrophic losses. Each step introduces a bottleneck. As energy increases, confinement becomes harder. Magnetic fields that easily trap low-energy particles become porous to high-energy ones. Acceleration times lengthen. Escape becomes more likely. The result is an exponential thinning of the population. This rarity is reflected in detection rates. At energies near the knee, detectors see many events per square metre per year. Near the ankle, that rate drops dramatically. At the highest energies, a single particle may strike a square kilometre only once per century. Observing such events requires patience and enormous detector arrays. The shape of the spectrum is therefore a balance sheet. It records how energy is injected, redistributed, and lost across the galaxy and beyond. The slope reflects acceleration efficiency. The knee reflects galactic limits. The ankle signals a transition to extragalactic space. The highest energy suppression encodes interactions with the fabric of the universe itself. Importantly, the spectrum is not static. Solar activity modulates the low-energy end, altering the flux reaching Earth over the 11-year solar cycle. Galactic conditions evolve over millions of years, slowly reshaping confinement and escape. Over cosmic time, the spectrum itself is a dynamic product of changing astrophysical environments. Yet despite this complexity, the overall power law form persists. This robustness is one of the most striking features of cosmic rays. It suggests that, across a vast range of conditions and sources, the same basic physical principles apply. Charged particles accelerated stochastically in turbulent magnetic environments naturally arrange themselves into this distribution. In this sense, the energy spectrum is a fingerprint of the processes that shape the high-energy universe. It does not identify individual sources, but it constrains the class of environments that can contribute. Any proposed source must not only accelerate particles to the required energies, but do so in a way that reproduces the observed spectrum after accounting for propagation and loss. The extreme end of the spectrum represents the frontier. These particles are so energetic that they challenge existing models. Their sources are rare, their paths only weakly scrambled, their interactions probing physics at energies unattainable in laboratories. They are few, but they carry disproportionate information. The vast majority of cosmic rays, however, inhabit the quieter slopes of the spectrum. They are numerous, persistent, and largely anonymous. Together, they form a background that is both mundane and extraordinary, a steady drizzle of high-energy matter shaped by explosions, fields, and distances far beyond Earth. The energy spectrum turns that drizzle into a narrative. It tells us that the universe accelerates particles continuously, that galaxies act as reservoirs and filters, and that only the most extreme environments contribute to the rarest events. It shows us not just how much energy cosmic rays have, but how the universe parcels that energy out, one particle at a time. At the extreme upper end of the cosmic ray spectrum, the universe produces particles that defy ordinary intuition. These are not incremental extensions of lower energy cosmic rays. They occupy a regime where familiar assumptions about acceleration, propagation, and even detectability begin to fail. An ultra-high energy cosmic ray can carry more kinetic energy than any particle produced by human technology, concentrated into a single proton or atomic nucleus. To appreciate the scale, it helps to compare. The most powerful particle accelerator ever built, the Large Hadron Collider, accelerates protons to energies of about 10 trillion electron volts per particle. Ultra-high energy cosmic rays exceed 100 quintillion electron volts. That is more than 10 million times greater. In macroscopic terms, a single subatomic particle can carry the kinetic energy of a fast-moving tennis ball. The difference is not merely quantitative. It places these particles in a category of their own. These events are extraordinarily rare. At such energies, the cosmic ray flux drops to a trickle. On average, only one particle per square kilometre reaches Earth per century. Detecting them requires instruments spread across vast areas, operating continuously for decades. When one is observed, it represents the culmination of an astrophysical process that is both rare and extreme. Ultra-high-energy cosmic rays are important not only because of their energy, but because of what that energy allows. At sufficiently high rigidity, magnetic fields lose their grip. These particles are deflected less during their journey through space. Their paths are not straight, but they are less tangled. For the first time in cosmic ray physics, directional information begins to re-emerge, at least in a statistical sense. This is why these particles sit at the boundary between cosmic ray physics and astronomy. They offer the possibility, still tentative, of tracing charged particles back to their sources. Yet even here, the universe imposes limits. As ultra-high energy cosmic rays travel through intergalactic space, they do not move through emptiness. Space is filled with low-energy photons, the most abundant of which come from the cosmic microwave background, the relic radiation left over from the early universe. For lower-energy particles, these photons are irrelevant. For ultra-high energy particles, they become obstacles. When a proton's energy exceeds a critical threshold, collisions with background photons can become violent enough to produce new particles. In particular, interactions between ultra-high energy protons and microwave background photons can create pions. This process drains energy rapidly. Each interaction reduces the proton's energy, and repeated interactions prevent it from traveling long distances without significant losses. This effect leads to a sharp consequence. The universe becomes opaque to ultra-high energy protons over cosmological distances. There is a maximum range from which such particles can arrive without losing their defining energy. This predicted suppression in the cosmic ray spectrum is known as the GZK cutoff, named after the physicists who independently identified the effect in the 1960s. The GZK cutoff does not mean that cosmic rays abruptly stop above a certain energy. It means that the highest energy particles must originate relatively nearby, on cosmic scales. Roughly speaking, sources beyond a few 100 million light-years cannot contribute significantly at the very highest energies, because the particles would lose energy along the way. This prediction was controversial for decades. Early experiments lacked the sensitivity and exposure to test it convincingly. Some datasets appeared to show events beyond the expected cutoff, fueling speculation about exotic physics or unknown particle properties. Over time, as detectors improved and statistics grew, a suppression consistent with GZK expectations emerged. The universe appears to enforce a horizon for ultra-high energy cosmic rays. This horizon narrows the field of possible sources, but it does not identify them. Several classes of astrophysical objects are capable, in principle, of accelerating particles to extreme energies. Among the most frequently discussed are active galaxies with supermassive black holes at their centers that actively accrete matter. In some cases, these systems launch relativistic jets that extend for thousands or even millions of light-years, channeling enormous amounts of energy into narrow beams. Within these jets, magnetic fields are strong, turbulence is intense, and spatial scales are vast. Shock fronts, shear layers, and magnetic reconnection events all provide potential acceleration sites. From a purely energetic standpoint, active galaxies have enough power to account for ultra-high energy cosmic rays. Another possibility lies in large-scale structure itself. As galaxy clusters form and merge, they generate enormous shock waves that propagate through intergalactic gas. These shocks are far larger than those in supernova remnants, though typically weaker in terms of speed. Whether they can accelerate particles to the highest observed energies remains uncertain, but they may contribute to the upper end of the spectrum. There are also more speculative candidates. Rapidly spinning neutron stars with intense magnetic fields could, under certain conditions, accelerate particles to extreme energies. Transient events, such as powerful flares or mergers, might provide brief but intense acceleration episodes. And there remains the possibility that some ultra-high-energy cosmic rays originate from sources or mechanisms not yet fully understood. What complicates the picture is composition. Ultra-high-energy cosmic rays are not necessarily protons. Observations suggest that, at the highest energies, heavier nuclei may play a significant role. A heavy nucleus carries more charge, which affects both its acceleration and its propagation. It is easier to accelerate to high energy in some environments, but it is also more fragile. Interactions with background photons can break the nucleus apart, altering both its energy and identity. This introduces ambiguity. A detected particle may not reflect the original particle that was accelerated. It may be a fragment produced during propagation. Tracing it back becomes even more difficult. Directional studies provide tantalizing hints but no definitive answers. Some analyses show weak correlations between the arrival directions of the highest energy cosmic rays and the distribution of nearby galaxies or active galactic nuclei. Other analyses find no statistically robust associations. The signals are subtle and the data sparse. Small changes in assumptions about magnetic fields or composition can change conclusions. Even with massive observatories such as the Pierre Auger Observatory, the challenge remains formidable. The detector can reconstruct the energy and approximate direction of incoming particles, but the journey those particles took through magnetic fields cannot be unraveled precisely. The maze has thinned, but it has not disappeared. This uncertainty is not a failure of technique. It is a reflection of the physics involved. Ultra-high energy cosmic rays probe environments where multiple unknowns overlap. Extreme acceleration, poorly mapped magnetic fields, rare events, and limited statistics. Each detected particle is precious, but each also carries limited information. What is clear is that these particles represent the most extreme end of natural particle acceleration. Whatever their sources, those sources must satisfy strict constraints. They must be powerful enough, large enough, and magnetically structured enough to accelerate particles without immediately losing them. They must be nearby enough to overcome energy losses during propagation. And they must exist in sufficient numbers to account for the observed flux. The fact that such particles exist at all is already a strong statement about the universe. It tells us that there are environments capable of pushing matter to energies far beyond what human engineering can achieve. It tells us that these environments are not singular anomalies, but recurring features of cosmic evolution. At the same time, the rarity of ultra-high-energy cosmic rays ensures that they remain elusive. They do not form a background. They are individual messengers, arriving sporadically, carrying clues that are incomplete and often ambiguous. Progress comes slowly, one event at a time, accumulated over years. In this regime, cosmic ray physics becomes an exercise in patience and inference. Each detection constrains models, narrows possibilities, and sometimes raises new questions. The sources remain uncertain, not because they are unknowable, but because the universe has arranged the problem to be difficult. These particles sit at the edge of what the cosmos allows. They test acceleration mechanisms to their limits. They test propagation through a universe filled with radiation and fields. And they test our ability to extract meaning from sparse, indirect signals. Ultra-high-energy cosmic rays are not just energetic, they are reminders that the universe operates comfortably in regimes far beyond everyday experience. Their existence is a fact. Their origins remain one of the most open questions in high-energy astrophysics. Once cosmic rays escape the magnetic confines of the Milky Way, they enter a different regime altogether. Inside the galaxy, their motion is dominated by tangled magnetic fields that trap them for millions of years. Beyond it, the density of matter drops sharply, magnetic fields weaken, and distances expand to scales where even relativistic particles begin to reveal the cost of long travel. Extragalactic space is not empty, but it is unforgiving. The first and most basic limitation on extragalactic cosmic rays is distance. Even travelling at nearly the speed of light, a particle crossing tens or hundreds of millions of light years is exposed to cumulative effects that cannot be ignored. Energy losses, deflections, and interactions that are negligible on galactic scales become decisive over intergalactic ones. As a result, only a small fraction of the universe is actually visible to us through cosmic rays. One limit arises from interactions with background radiation. Intergalactic space is filled with photons, most prominently those of the cosmic microwave background, and the diffuse infrared and optical backgrounds produced by stars and galaxies. For low and moderate energy cosmic rays, these photons are irrelevant. For ultra-high energy particles, they become obstacles. Collisions can rob the cosmic ray of energy or fragment it entirely, shortening the distance it can travel while retaining its original energy. This creates an effective horizon. Even if a source exists on the far side of the observable universe, its highest energy cosmic rays will never reach Earth intact. They will arrive degraded, shifted to lower energies, or not arrive at all. The observable extragalactic cosmic ray sky is therefore local in a cosmic sense, limited to a relatively small volume around our galaxy. Magnetic fields introduce a second constraint. Intergalactic magnetic fields are much weaker than galactic ones, but they extend across immense distances. Their precise structure is still poorly known. They may be concentrated along filaments of large-scale structure, amplified near galaxies and clusters, and extremely weak in cosmic voids. For a charged particle, even a weak field can produce substantial deflection if the path length is long enough. These deflections introduce time delays. A photon emitted from a distant galaxy arrives at Earth along the shortest path, taking a time determined almost entirely by distance. A cosmic ray emitted at the same moment follows a longer, curved trajectory, wandering through magnetic irregularities. Its arrival can be delayed by thousands, millions, or even tens of millions of years relative to the light. This decoupling of arrival times has important consequences. Cosmic rays cannot be associated with transient events in a straightforward way. A flare, explosion, or merger observed in light today may have emitted cosmic rays that will not arrive until far in the future, or may have arrived long before the light we see now. Temporal coincidence is lost. Time delays also smear out variability. Even if an extragalactic source emits cosmic rays in bursts, Earth receives them as a steady drizzle spread across immense timescales. This further reinforces the isotropy of the cosmic ray sky and obscures individual sources. Despite these challenges, certain classes of extragalactic objects remain compelling candidates for producing cosmic rays beyond galactic energies. Active galactic nuclei, powered by accreting supermassive black holes, release enormous amounts of energy into their surroundings. Their jets can extend far beyond the host galaxy, driving shocks and turbulence capable of accelerating particles. The sheer scale of these systems makes them natural contenders. Starburst galaxies represent another possibility. These galaxies form stars at rates far higher than typical, leading to frequent supernova explosions, intense stellar winds, and highly turbulent interstellar environments. Individually, their accelerators may resemble those in the Milky Way. Collectively, operating at much higher intensity, they may push particles to higher energies, or inject large populations of cosmic rays into intergalactic space. Connections between cosmic rays and such sources are not established through direct imaging, but through statistical inference. Researchers look for correlations between the arrival directions of the highest energy cosmic rays and the distribution of nearby galaxies, active nuclei, or regions of enhanced star formation. The signals are subtle. Any genuine correlation must rise above the background of magnetic deflection and limited statistics. Isotropy provides one of the strongest constraints. Over most of the energy spectrum, cosmic rays arrive nearly uniformly from all directions. This uniformity implies either a very large number of distant sources distributed throughout space, strong magnetic scrambling, or both. A single dominant nearby source would produce a detectable anisotropy unless its signal were heavily smeared by magnetic fields. At the highest energies, where deflection is reduced, small deviations from isotropy begin to appear. These deviations are weak, but they are measurable with large datasets. They suggest that ultra-high energy cosmic rays are not entirely random in origin, but reflect the large-scale structure of the nearby universe. Clustering analyses show that arrival directions may align loosely with the distribution of matter on tens of millions of light-years scales. Clustering, however, is not pointing. Even when clusters of arrival directions are identified, they rarely correspond cleanly to a single astrophysical object. Instead, they trace regions of enhanced galaxy density, filaments, or groups. This is consistent with a picture in which many sources contribute, each blurred by magnetic deflection rather than a small number of sharply defined emitters. Composition again complicates interpretation. If extragalactic cosmic rays are primarily protons, they retain more directional information. If they are heavier nuclei, deflections increase and horizons shrink due to fragmentation. Observations suggest that composition may change with energy, implying that the cosmic ray sky is not uniform in particle type. Any attempt to associate arrival directions with sources must account for this mixture. Another constraint comes from energetics. Any proposed extragalactic source population must supply enough energy to sustain the observed cosmic ray flux. This requirement eliminates many otherwise plausible candidates. The total power injected into cosmic rays must match what is observed locally after accounting for propagation losses. Active galaxies and starburst galaxies pass this test. Many other sources do not. Extragalactic cosmic rays therefore occupy a narrow window. They must be produced by powerful, relatively common sources within a limited distance. They must survive propagation through radiation fields and magnetic structures, and they must collectively produce a sky that is nearly isotropic with only faint imprints of structure. This combination explains why identifying individual sources has proven so difficult. The information is there, but it is encoded statistically rather than directly. Cosmic rays beyond the Milky Way tell us about populations and environments, not about specific events. They also reveal something about the universe at large. Their propagation depends on magnetic fields that are otherwise invisible. Their horizons depend on background radiation fields that fill all of space. Their arrival patterns reflect the distribution of matter on the largest scales. In this way, cosmic rays become probes of the cosmic web itself. Unlike light, which travels cleanly and preserves images, cosmic rays trade clarity for reach. They carry information from regions and processes that may be faint or obscured in electromagnetic radiation. But that information arrives, scrambled, delayed, and diluted. Extracting meaning requires patience, large detectors, and careful statistics. Beyond the Milky Way, cosmic rays are no longer just messengers from individual accelerators. They are tracers of cosmic environments. They reveal how energy flows through galaxies, how magnetic fields shape intergalactic space, and how extreme processes contribute to the high-energy universe as a whole. Their journey to Earth is long, indirect, and lossy. That journey erases many details, but it leaves behind constraints that no other messenger provides. Within those constraints lies the story of cosmic rays beyond our galaxy, a story written not in images but in distributions, limits, and subtle deviations from uniformity. Cosmic rays are usually discussed in the language of astrophysics, energies, spectra, sources, but their influence does not stop at the edge of the atmosphere. They intersect with biology, aviation, and the long history of life on Earth in quiet, indirect ways. Their effects are rarely dramatic. They accumulate, modulate, and occasionally leave marks that are only visible over long timescales. At ground level, cosmic rays contribute only a small fraction of the natural background radiation that humans experience. Most of that background comes from radioactive elements in Earth's crust and from radon gas. The atmosphere and the planet's magnetic field do an effective job of filtering out the most energetic primary particles. What reaches the surface is dominated by muons and a small number of secondary particles. The resulting radiation dose is low, stable, and unavoidable. That balance changes with altitude. As elevation increases, the shielding provided by the atmosphere decreases. At around 10 kilometers or about 6 miles, the typical cruising altitude of commercial aircraft, the cosmic ray intensity is several times higher than at sea level. The air is thinner, and more of the secondary particle cascade survives. Muons are more numerous. Neutrons produced in atmospheric interactions become significant contributors to radiation dose. For passengers on occasional flights, this increase is negligible. For flight crews, it is not. Pilots and cabin crew spend hundreds or thousands of hours per year at altitude. Over a career, their cumulative exposure to cosmic radiation can rival or exceed that of some ground-based radiation workers. For this reason, occupational radiation exposure for aircrew is monitored in many countries, and flight routes are sometimes adjusted during periods of intense solar activity to manage exposure. Solar activity adds complexity. While cosmic rays originate outside the solar system, their intensity at Earth is modulated by the solar wind and the sun's magnetic field. During periods of high solar activity, the strengthened solar magnetic field partially shields the inner solar system from lower energy galactic cosmic rays, reducing their flux at Earth. During solar minimum, this shielding weakens and cosmic ray intensity increases. At the same time, solar eruptions can produce bursts of energetic particles of their own. These solar energetic particle events can temporarily raise radiation levels at flight altitudes, especially on polar routes where Earth's magnetic field provides less protection. Modern aviation systems monitor space weather precisely because these events, though rare, can have measurable biological and electronic effects. Beyond the atmosphere, the situation changes dramatically. Astronauts in low Earth orbit are partially shielded by Earth's magnetic field, but not completely. They experience higher cosmic ray fluxes than any population on the ground. Outside that magnetic shield, on missions to the Moon or beyond, the exposure increases further. Galactic cosmic rays become a dominant radiation hazard, especially because of their high energies and penetrating power. Unlike X-rays or gamma rays, high-energy cosmic rays can traverse shielding materials and deposit energy deep inside tissues. They produce complex damage tracks at the cellular level, increasing the risk of cancer and other long-term health effects. Managing this risk is one of the central challenges of human deep space exploration. Space agencies, including NASA, devote significant effort to modelling cosmic ray exposure and developing shielding strategies. However, shielding against high-energy particles is fundamentally difficult. Adding more material can sometimes make the problem worse by generating additional secondary radiation when cosmic rays interact with the shielding itself. There is no simple barrier. The problem must be managed rather than eliminated. On Earth, the biological effects of cosmic rays are subtle but persistent. One of the most discussed and controversial topics is their possible influence on cloud formation and climate. The basic idea is straightforward. Cosmic rays ionize the atmosphere. Ions can act as nucleation sites around which water vapor condenses. In principle, changes in cosmic ray intensity could influence cloud cover, which in turn affects Earth's energy balance. This hypothesis has been explored extensively, both observationally and experimentally. Laboratory studies have shown that ionization can enhance the formation of tiny aerosol particles under certain conditions. However, whether these particles grow large enough to influence cloud properties in the real atmosphere is still debated. Climate systems are complex, influenced by many competing factors. Isolating the role of cosmic rays has proven difficult. What is clear is that any climatic effect, if it exists, is modest. Cosmic rays do not drive climate change on their own. At most, they may act as a secondary modulator under specific conditions. The scientific debate continues, not because the idea is dramatic, but because it sits at the intersection of atmospheric chemistry, solar physics, and particle interactions, a region where uncertainties remain. On longer timescales, cosmic rays intersect with life in a different way. High-energy particles can damage DNA, causing mutations. Most such damage is repaired by cellular mechanisms. Occasionally, repairs are imperfect. Over generations, these rare events contribute to genetic variation. Cosmic rays are not unique in this role. Natural radioactivity, ultraviolet light, and chemical processes all contribute, but they are part of the background against which evolution operates. There is no evidence that cosmic rays directly drive evolutionary change in any targeted or directional way. They do not encode information or guide adaptation. Their role is statistical. They add noise to the genetic system. Over geological timescales, that noise becomes part of the raw material on which natural selection acts. Some researchers have explored whether variations in cosmic ray intensity over Earth's history due to changes in solar activity, geomagnetic field strength, or the solar system's motion through the galaxy could have influenced biological evolution indirectly. These ideas are speculative and difficult to test. The fossil record is incomplete. The timing of cosmic ray variations is uncertain. Correlation does not imply causation. What can be said with confidence is more modest. Life on Earth evolved in the presence of cosmic radiation. Biological systems adapted to repair damage, tolerate low levels of mutation, and function under constant exposure. Cosmic rays are not external anomalies imposed on life. They are part of the environment in which life arose. This perspective reframes the question. Instead of asking whether cosmic rays affect life, it becomes clear that life has always existed within a cosmic ray field. The atmosphere, magnetic field, and biosphere co-evolved in a way that mitigates risk while allowing complexity to flourish. Occasional increases in radiation due to altitude, space travel, or rare astrophysical events push that balance, but do not define it. From a human standpoint, the relevance of cosmic rays is practical rather than existential. They matter for aviation safety, space exploration, electronics reliability, and long-term health risk assessment. They are a design constraint, not a threat. Engineers account for them, biologists study their effects, mission planners work around them. From a broader perspective, cosmic rays are reminders that Earth is not isolated. The boundary between space and life is porous. High-energy particles cross it continuously, mostly unnoticed, occasionally consequential. The same processes that shape galaxies and accelerate particles also touch biology in indirect ways. There is no dramatic narrative here. Cosmic rays do not trigger extinctions on their own. They do not rewrite genomes overnight. Their influence is incremental. It accumulates over time, diffused across populations and generations. That is precisely why it is difficult to study and why it is easy to overlook. Yet their presence is constant. Every organism alive today exists beneath a sky that is not just illuminated by starlight, but threaded with energetic particles from distant astrophysical events. Life has never experienced a radiation-free universe. It has adapted to one that is quietly active. In this sense, cosmic rays occupy a middle ground between astrophysics and biology. They are not central actors in the story of life, but they are part of the background conditions that shape it. They remind us that the processes governing the universe at its largest scales do not stop at the edge of the atmosphere. They continue subtly into the realm of living systems. The influence of cosmic rays on life is not a headline. It is a footnote written across millions of years. Small, persistent, and inseparable from the environment in which life evolved. Cosmic rays arrive without images, without timestamps, without clear directions. They do not behave like light, and that is precisely why they matter. They carry information that photons cannot. They come from environments that are opaque to electromagnetic radiation, from processes that do not shine efficiently, and from energies where light is no longer the dominant messenger. In the high-energy universe, cosmic rays reveal a different layer of reality. Light is an excellent tracer of temperature, composition, and structure. It tells us where stars are burning, where gas is cooling, where matter is dense enough to glow. But light fails in violent, compact, or magnetically dominated environments. In shock fronts, relativistic jets, dense stellar cores and turbulent plasmas, charged particles can be accelerated without producing much radiation. Energy can flow into motion rather than photons. Cosmic rays emerge from exactly these conditions. This makes them probes of acceleration itself. A photon tells us that something is hot or luminous. A cosmic ray tells us that something can accelerate matter to relativistic energies and hold it there long enough for escape. The existence of cosmic rays proves that the universe contains natural particle accelerators, operating far beyond anything humans can build. Their energy spectrum, composition, and abundance constrain how those accelerators work, even when their locations remain hidden. Cosmic rays also interact differently with matter. When they collide with gas, they produce secondary particles that light cannot create directly. These interactions generate neutrinos and gamma rays in linked processes. As a result, cosmic rays sit at the center of what is now called multi-messenger astrophysics, the combined study of photons, particles, and space-time disturbances. Neutrinos are especially important in this context. When high-energy protons interact with matter or radiation near their sources, they produce charged and neutral pions. Neutral pions decay into gamma rays. Charged pions decay into muons and neutrinos. Gamma rays can be absorbed or scattered. Neutrinos are not. They travel in straight lines from their sources, passing through stars, planets, and entire galaxies without deviation. Detecting high-energy neutrinos allows scientists to identify sites of hadronic acceleration, places where protons and nuclei, not just electrons, are being energized. This is crucial because electrons alone cannot explain the cosmic ray population that reaches Earth. Facilities such as IceCube Neutrino Observatory have begun to detect neutrinos with energies high enough to be associated with cosmic accelerators beyond the solar system. In a few cases, neutrino detections have coincided in direction with active galaxies observed in gamma rays, strengthening the link between cosmic rays and specific astrophysical environments. Gravitational waves add another layer. They trace the motion of massive objects, black holes, neutron stars, merging systems, independent of electromagnetic emission. When a gravitational wave event is detected, it identifies a site of extreme gravity and energy release. If such events also produce cosmic rays or neutrinos, then multiple messengers together can reveal the full chain of energy flow: gravity driving motion, motion accelerating particles, particles producing secondary radiation. So far, direct associations between gravitational wave sources and cosmic rays remain elusive. Time delays caused by magnetic deflection make coincidence difficult. A merger observed today could produce cosmic rays that arrive thousands or millions of years later, but the conceptual connection is firm. Cosmic rays are part of the same high-energy ecosystem as gravitational waves and neutrinos. Together, they describe processes that cannot be captured by light alone. Despite more than a century of study, major mysteries remain. The precise origin of the highest energy cosmic rays is still unknown. We know they must come from nearby extragalactic sources. We know they require extreme conditions, but no individual source has been unambiguously identified. Magnetic fields blur paths. Composition complicates interpretation. Statistics remain limited. The question is not whether the sources exist, but why they remain so difficult to isolate. Another open question concerns composition across the energy spectrum. How the mix of protons and heavier nuclei changes with energy carries information about both acceleration and propagation. Current measurements suggest transitions, but uncertainties remain. Resolving this requires better detectors, longer observation times, and improved models of particle interactions at energies beyond laboratory reach. There is also the question of propagation itself. Galactic and intergalactic magnetic fields are still poorly mapped. Cosmic rays are among the few probes sensitive to these fields, yet interpreting their behavior depends on knowing the very structures they are meant to reveal. This circularity is one of the central challenges of the field. Progress comes through iteration, models constrained by data, data interpreted through models slowly converging. On the particle physics side, cosmic rays test interactions at energies far above those produced in accelerators. Air shower observations depend on extrapolating known physics into unknown regimes. Discrepancies between simulations and measurements may hint at new phenomena, or they may reflect gaps in understanding of hadronic interactions. Cosmic rays therefore remain relevant not only to astrophysics, but to fundamental physics itself. What makes cosmic rays enduringly important is not any single mystery, but their position at the intersection of disciplines. They connect stellar evolution to galactic structure, magnetic fields to particle physics, astrophysical explosions to biological exposure. They are shaped by processes operating across scales from subatomic to cosmological. They also impose humility. Cosmic rays remind us that much of the universe does not announce itself in ways that are easy to observe. Some information arrives scrambled, some arrives late, some arrives without context. Extracting meaning requires patience, statistics, and an acceptance that clarity is not guaranteed. Yet the payoff is real. From cosmic rays came the discovery of new particles, the realization that galaxies are energetic systems, the recognition that space is magnetized and active. They helped shape modern astrophysics long before space telescopes existed. They continue to do so now, complementing observations across the electromagnetic spectrum. Cosmic rays are not a replacement for light, they are a counterpoint. Where light shows structure, cosmic rays show process. Where light traces surfaces, cosmic rays trace engines. Where light gives images, cosmic rays give constraints. Their message is not pictorial, it is statistical, indirect, and often frustrating. But it is also unique. Without cosmic rays, our picture of the high-energy universe would be incomplete. We would see where energy is radiated, but not where it is stored, transferred, and concentrated into motion. More than a century after their discovery, cosmic rays remain active messengers. They continue to fall through Earth's atmosphere, pass through detectors, and challenge interpretation. They carry evidence of shocks, fields, and accelerators that cannot be studied any other way. In modern astrophysics, they are no longer curiosities. They are boundary markers, signals that the universe operates comfortably beyond familiar limits, accelerating ordinary matter to extraordinary extremes and delivering that matter to Earth one particle at a time.